Next, let's solve one example using forward difference operator. If h is very small, prove that delta to the power n plus 1 f of x0 is equivalent to h to the power n plus 1 f of n plus 1 x0. This notation means n plus 1th time derivative of f at the point x0. We have to prove it if h is very small. Now we are starting with f dash x0, as we have to go for the n plus 1th derivative starting with the first one. This means limit h tending to 0, f of x0 plus h minus fx0 divided by h. This is from the preliminary definition of differentiability. Now this part can be written as delta of fx0, right? This is our forward difference operator, divided by h. Now it is given that h is very small. That means from there we can write delta of fx0 is equivalent to putting h on that side, h into f dash x0, because this is the limiting value, but still it is given that h is very small, so we can write this value will be equivalent to h into f dash x0. Again we have delta f of double dash x0. Its definition is limit h tending to 0, f dash f of x0 plus h minus f dash x0 divided by h. Now what we can write for the upper part? Using this relation, we can write f dash x0 plus h as delta of f of x0 plus h by h minus delta of f of x0 by h, right, whole divided by h. So it will become limit h tending to 0, delta f of x0 plus h minus delta f of x0 by h square. That is, from there we can write that delta squared f of x0, this part will become, if you take delta, then it will become f of x0 plus h minus fx0. That means delta of fx0. So ultimately delta square fx0, this is equivalent to h square into f double dashed x0. Okay, this is what we got from the second step. Now similarly, by applying nth step, what we can write? Delta to the power n f of x0 is equivalent to, we want to find out the n plus 1th, so we are taking the n plus 1th. Delta to the power n plus 1 fx0 is equivalent to h to the power n plus 1 into f of n plus 1th derivative at the point x0. This one, this gives the result. Okay. Next one is few another operators. Next operator is called shift operator. Shift operator, and this is known as, denoted as capital E, this one, and defined as E of fx. From the name it is quite clear that it is shifting something. That means just it is shifting fx to its next value. What is the next value of fx? This is f of x plus h. So E of fx is f of x plus h. Okay, that means E of fx0, it will be f of x0 plus h, that is f of x1 ultimately. Okay. Next operator is called difference operator or differential operator. Differential operator is denoted by d and defined as the derivative of the function, that is d of fx is equals d dx of fx. It's just the difference operator, that is differential operator. Next is called average operator, and it is denoted by mu and defined by mu of fx equals half of f of x plus half h plus f of x minus half h. Average means taking the average value, So we are considering f of x plus h, then taking the half value from the left and half value from the right, add them, divided by 2. This is called average operator. And the next one is called central difference operator. Central difference operator. And it is denoted by delta, small delta, and defined as delta of fx equals f of x plus half h minus f of x minus half h. This is called central difference operator. So we got total 6 operators. Number 1 was forward difference operator denoted by delta, then backward difference operator denoted by backward delta, then shift operator E, then differential operator D, then average operator mu, and the central difference operator delta. Okay, among all these three, these first 3 are very much important, always useful, these first 3. Okay, now we have to find out few relations between them, that is how these all operators are related. So let's start to find few relations between them. First property or the first relation is E dot delta equals delta dot E. So starting with E dot delta, as actually not equals, we can write equivalent because they are operators like mapping. So we cannot write a mapping f equals g, we have to write f equivalent to g. We can write fx equals gx because these are the values. Now for operator we use this equivalent sign. So E dot delta equivalent to delta dot E. That means E and delta are commutative with each other. So starting with this over fx, some argument or entries, that is E of delta fx. Applying delta fx, this will become this, that is E of f of x plus h minus E of fx, E of x plus h, this becomes f of x plus 2h minus E of fx equals f of x plus h. Now what does it mean by f of x plus 2h? Minus f of x plus h, this means delta of f of x plus 2h, right? That means just taking its next value minus the current value. So next value is x plus 2h minus current value is x plus h. That means this is delta of f of x plus h. And f of x plus h means E of fx, that is delta dot E fx. So we have started with E dot delta and we get delta E. So E dot delta equals delta dot E, equivalent to this one. Next, there is another the relation between E and delta. This is one property. Next property is relation between E and delta. Now E of fx means f of x plus h, right? And of delta of fx, this becomes f of x plus h minus fx. So here it means E of fx minus fx, taking fx common, so E minus 1 fx. That means from there we can write delta is equivalent to E minus 1. Okay, or E is equivalent to delta plus 1. This is the required relation between E and delta. Similarly, we can find the relation with the backward operation also. It will become the backward delta equals 1 minus E inverse. This one. And E inverse means, what does it mean by E inverse? E was shifting operator and it becomes the inverse shifting operator. For shifting operators, it shifts the value to the next one. So for the inverse shifting operator, it will shift the value to the previous one. That is E inverse of fx, it will take the value f of x minus h. Okay. So these are the two relations with forward delta and backward delta and E. These two are very important, very much useful actually. Next property is delta dot delta equals delta minus backward delta. This one. You can prove it by the definition of these two operators, that is forward and backward delta, or we can prove it using the concept of E. Using the concept of E, it will be easier proving. So delta is equals E minus 1 and this delta is equivalent to 1 minus E inverse, right? So starting with this, putting their values, this will become E into E inverse, that is 1 plus E inverse, keeping this one in bracket, and then this is forward delta and this is backward delta. Okay, so delta dot delta becomes this. This proves the result. Next, find out the relation between the difference operator and the delta operators, that is between D and capital delta. Now we will apply here Taylor's theorem. Is f of x plus h, applying over f of x plus h, applying Taylor's theorem. So we will get fx plus h f dash x plus h square by factorial 2 f double dash x plus h cube by factorial 3 f triple dash x, and so on, right? Keeping this one as fx. Okay, at first take the left one. What we can write? We can write it is E of fx, shifting operator, equals, this is fx plus f dash x means d of fx, that is d of fx plus h square by factorial 2, there was one h square by factorial 2, then d square fx plus h cube by factorial 3, d to the power 3 fx, and so on, right? Now for E, what we can write? 1 plus delta fx equals, the right hand side can be written as, taking fx common, 1 plus hd plus h square by factorial 2d square plus dot dot into fx, right? Now what is the value of this series? This takes the value e to the power x, that means e to the power hd fx. So from there we can conclude 1 plus delta, this operator, is equivalent to e to the power hd, right? Now taking common log, taking log on both sides, so it will become log 1 plus delta and it will become log e to the power hd, that means ultimately hd. So hd equals log 1 plus delta, expanding the log series. So what will we get? It will become delta minus delta square by factorial 2, not factorial 2, only 2. For logarithmic series we got only the 2, that is plus delta cube by 3 minus delta to the power 4 by 4 plus, and so on. That means d equals 1 by h, then in bracket delta minus delta square by 2 plus delta cube by 3, and so on. This is the required relation between D and delta. Okay. Similarly, we can find out the relations between the shifting operator and the average operator, or the another operators which are called central difference operators, and so on. Next, proof another one property. Prove that 1 plus delta square by 4 is equivalent to mu square. This is a relation between mu and delta. So at first take this definition of these two operators. Delta. This is called central difference operator, and its value is delta of fx was f of x plus half h minus f of x minus half h. So how we can express this operator using e or using shifting operator? We can write it as e to the power half h minus e to the power minus half h. Sorry, not h, fx. Right? This quantity can be written as e to the power half fx. So from there what we can write, delta is equivalent to e to the power half minus e to the power minus half. Similarly, for the next operator, which is called mu, that means the average operator, what we can write, just by applying the same procedure, we can write mu equals e to the power half plus e to the power minus half whole divided by 2. Okay, this is the relation between these two operators, this and this, using shifting operators. Now we will use that values to prove this result. So if we use it, what will we get? Starting with the left hand side, 1 plus delta square by 4. That means 1 plus e to the power half minus e to the power minus half its square by 4. So 1 plus, expanding this, e plus e inverse minus 2 by 4. That means it will ultimately become e plus e inverse plus 2 by 4. That is e to the power half plus e to the power minus half its whole square by 4. That is ultimately it will become mu square. Because mu takes this value, we can write it to its whole square. So it will become mu square. So this proves the result.